A national defense laboratory in Beijing has successfully developed a handgun-sized miniature, traveling wave tube, TWT, with an output power exceeding 500 watts, reaching a level previously only achievable by large equipment. They will provide a broadband high frequency that can cover the X-to-Q band, 818 GHz. The power traveling wave tube has been compressed to a height of only 20 millimeters. According to the disclosed information, this is less than half the thickness of similar Western products, but it achieves performance surpassing. At present, the mainstream technology route is solid-state power amplifiers, SSPs, based on wide-bandgap semiconductors such as gallium nitride, GaN, solid-state technology. The technology has brought great advantages: small size, high reliability, easy large-scale integration, and has given birth to the modern ESA radar revolution, allowing radar beams to perform almost instantaneous electronic scanning and multi-target tracking. However, solid-state amplifiers also have inherent bottlenecks. At extremely high frequencies and wide bandwidths, the output power of a single solid-state device is limited. In order to obtain sufficient total power, a ESA radar typically requires the integration of thousands of transmit-receive (TR) modules, each module containing an independent solid-state amplifier. The device. This is where the strategic value of traveling wave tubes lies. A traveling wave tube can be regarded as a force multiplier. It can generate peak power of several kilowatts, or even higher with a single device, and can cover an extremely wide frequency range. An electronic warfare aircraft equipped with a powerful jamming machine based on traveling wave tubes. It can effectively blind enemy radar and communication systems in the distance, opening up a safe air corridor for our own attack fleet. Therefore, countries such as China and the United States are actually adopting a dual-track parallel strategy. On the one hand, vigorously developing solid-state technologies represented by gallium nitride for building flexible and multifunctional ESA systems. On the other hand, continuous improvement in research and development of vacuum electronic technology, represented by traveling wave tubes, as a means of achieving limits. The killer of power output. This architectural change will bring a series of tactical advantages. Further detection range. The detection range of a radar is proportional to the square root of the transmitted power. The significant increase in power will enable fighter jets, ships, and early warning aircraft to detect threats, including stealth targets, earlier and take the initiative on the battlefield. Stronger anti-interference ability. Higher output power means that radar signals have a higher signal-to-noise ratio when facing enemy electronic interference and are more difficult to suppress. Meanwhile, radar itself can also serve as a powerful electronic attack weapon to burn through enemy sensors. Multifunctional integration. A high-power, broadband or F-front end that can not only be used for radar detection, but also perform various tasks such as electronic interference, target high-gain communication, and even directed energy weapons. High-power microwave, achieving high hardware integration and software-defined functionality. For stealth fighter jets such as the J-20, installing more powerful radar and electronic warfare systems can give them a decisive advantage in detecting and attacking their opponent's stealth fighters first.